Part 1. Picture a silent night at a mountaintop observatory. The air is sharp and cool, and above you stretches a deep, inky sky, like dark velvet sprinkled with countless shimmering stars. Astronomer Saul Perlmutter sits at the telescope, eyes locked on the glowing screen where data from distant supernovae is pouring in, exploding stars that light up the cosmos like giant fireworks. It is the year 1998, and Saul and his team expect to confirm what everyone already knows. The universe is expanding, but gravity is gradually slowing it down, like an invisible hand gently pulling on the reins of a galloping horse. Then the numbers appear, and they refuse to make sense. The supernovae are flying away faster than they should. The universe is not slowing down, it is speeding up, ripping itself apart with relentless force. Saul blinks, rereads the calculations, but there is no error. This single moment changes everything humanity thought it knew about the cosmos. What if everything we believed about the fate of the universe was wrong? What if an invisible force hidden inside the emptiness of space itself is pushing galaxies away from each other, like invisible hands slowly tearing the walls of a room apart? This force is called dark energy, a mysterious presence that makes up nearly 70% of everything that exists. It does not shine, it does not warm, it does not touch us directly, yet its power is overwhelming. Picture standing on a beach when the ocean suddenly starts receding, not because of the tide, but because the very ground beneath your feet is stretching. That is exactly what dark energy is doing to space-time, stretching it, forcing everything to fly apart faster and faster. Let us go back to that exact moment. Saul Perlmutter, Adam Rees, and Brian Schmidt were trying to measure the expansion rate of the universe. They used Type 1a supernovae, stars that explode with almost exactly the same brightness, acting like perfect standard candles in the sky. The dimmer the supernova, the farther away it is. They expected distant supernovae to appear brighter than predicted if expansion was slowing down. Instead, the supernovae were fainter, meaning they were farther away than anyone thought. The expansion is accelerating. The numbers are brutal. For every megaparsec, about 3.26 million light-years, the recession speed increases by 74 kilometers per second. A galaxy 10 megaparsecs away is racing from us at 740 kilometers per second, and that number keeps growing. Visualize it like a movie. The screen fills with a star field. Galaxies drift slowly at first, then suddenly the pace quickens. They scatter like leaves in a hurricane. The soundtrack drops to a deep rumble that builds into a roar, the sound of invisible power tearing space itself. Think about the scale. In a few billion years, if dark energy keeps winning, every galaxy beyond our small local group will disappear forever behind the cosmic horizon. Their light will never reach us again. The night sky will become empty. We will be left alone in a cold, dark void. This is not science fiction. This conclusion comes straight from the Hubble Space Telescope, from precise measurements of redshift, light stretched by the expanding universe. But where does this energy come from? Scientists call it dark because it is invisible. It's like a ghost in an old house. You feel the cold draft, you see objects move, but the ghost itself never appears. In Einstein's equations of general relativity, there is a term called the cosmological constant, something Einstein added in the year 1917 to keep the universe static, then angrily called his greatest blunder. Now that same constant has returned as the perfect explanation. It is the energy of empty space itself. In quantum mechanics, the vacuum is not empty at all. It boils with virtual particles that pop into existence and annihilate in the blink of an eye, creating positive energy that pushes space apart. Simple everyday analogy, take a rubber balloon and inflate it. The dots drawn on its surface move away from each other. That's cosmic expansion. Now imagine the balloon is inflating by itself, faster and faster, without anyone blowing air into it. That self-inflation is dark energy. Its density is tiny, 10 to the power of minus 27 kilograms per cubic meter. But because it's everywhere, the total effect is colossal. The amount of dark energy inside an ordinary bedroom equals the energy of tens of suns in every cubic light year. The existential question hangs in the air. Why is this happening? Dark energy took over roughly 9 billion years ago, when the expansion switched from deceleration, driven by gravity of matter, to acceleration. The universe was born 13.8 billion years ago in the Big Bang, a hot, dense fireball. Now it's cooling, stretching into what exactly? What if dark energy isn't constant? If it grows stronger, we head toward the Big Rip, a future in which even atoms are torn apart. If it weakens, we collapse. These ideas feel like nightmares in which reality itself is coming undone at the seams. The scientific community's first reaction was pure shock. Maybe our measurements are wrong, but the data kept piling up. The Planck satellite measured the afterglow of the Big Bang, the cosmic microwave background, and proved the universe is flat, with exactly the critical density needed for flatness. To make the numbers work, dark energy must be 68% of everything, dark matter 27%, and ordinary matter, stars, planets, you and me, only 5%. We are the tiny visible tip of an enormous invisible iceberg. History adds drama. Einstein introduced the cosmological constant to keep the universe static. Edwin Hubble discovered expansion in the year 1929, and Einstein dismissed his own constant. Then, in 1998, it came roaring back. The 2011 Nobel Prize in Physics was awarded to Perlmutter, Rees, and Schmidt for proving that the universe is accelerating. Picture the animation. Galaxies like raisins in rising dough, but the oven keeps getting hotter and the dough expands exponentially. Add the human touch. Saul Perlmutter later said in an interview, "We checked the data for weeks, refusing to believe our own eyes. It felt like discovering a new law of nature." And now the provocation. What if dark energy is leaking from parallel universes? Or perhaps gravity itself is wrong, as some modified gravity theories suggest. Data from the Sloan Digital Sky Survey show Baryon acoustic oscillations, ancient sound waves frozen in the distribution of matter, that perfectly match an accelerating universe. The distance to the surface of last scattering is 46 billion light-years in co-moving coordinates. Compare the scale. The energy of dark energy is roughly the mass of 1 proton per cubic meter, smaller than a single electron's energy, yet on cosmic scales, it equals the mass energy of entire galaxies multiplied billions of times over. Philosophically, it feels like Descartes doubting everything, only now we're doubting the very fabric of reality. The universe is not a cold machine. It is alive, breathing, hiding dark secrets. This is only the beginning of our journey. The evidence is mounting, from observations to theories, from the past to the future. We tiny humans dare to stare into the abyss, and the abyss stares back. Get ready. Our adventure is just beginning. Part 2. Discovery. Imagine, in the year 1998, in a quiet laboratory where computer screens flicker in the dim light, a group of astronomers huddles over fresh data. Saul Perlmutter, the head of one team, stares at the graphs that have just come in from the telescopes. He and his colleagues notice something strange. Distant supernova stars, these cosmic explosions, are moving away from us not as expected. Instead of slowing down under the weight of gravity, like a ball that, reaching the top, starts to fall down, the universe is accelerating. It was as if someone was pushing that ball upward, not letting it stop. Saul and his team, working on a project to search for supernovae at great distances, could not believe their eyes. They checked the calculations over and over, but the data stubbornly showed the expansion of the universe is gaining speed. Let us break down the fundamental principle that underlies all this. The universe began with the Big Bang, a massive explosion of energy and matter that happened 13.8 billion years ago. Since then, space has been expanding, carrying galaxies away from each other. It is like drawing dots on a balloon and starting to inflate it. The dots move apart, but not because they are moving themselves, but because the surface of the balloon is stretching. Edwin Hubble, in the year 1929, discovered this fact by observing the redshift of light from distant galaxies. The light stretches like the sound of a siren from a receding car, becoming redder. Gravity, this invisible force of attraction, should have eventually slowed down the expansion because all matter in the universe pulls each other back. But the supernova data showed the opposite. A simple analogy from everyday life. Imagine throwing a stone upward. It flies fast, but Earth's gravity slows it down, and eventually it falls. Similarly with the universe. After the Big Bang, it expands quickly, but gravity should break the process. However, in 1998, two teams, one led by Perlmutter, the other with Adam Rees and Brian Schmidt, discovered that distant supernovae are dimmer than expected. This means they are farther away than they should be in a decelerating expansion. The distances to these supernovae are billions of light years. The light has been traveling to us for billions of years. If the expansion is accelerating, then in the past it was slower and the light covered shorter distances, but now space has stretched more, making the objects dimmer. The central mystery here is the paradox of anti-gravity. Gravity attracts, but something repels. It is like if in your room the furniture suddenly started sliding to the corners without any visible reason. Scientists introduce the term dark energy, an invisible, all-pervading force that counteracts gravity on enormous scales. It does not interact with ordinary matter like light or electromagnetism, but its effect is visible in the movement of galaxies. The density of this energy is constant, unlike matter, which dilutes as it expands. This means that as the universe grows, dark energy becomes dominant. Imagine a jar with water and oil. Water is matter that settles. Oil is dark energy that stays on the surface. The reaction of the scientific community was stormy. At first, skepticism. Maybe the supernovae are not as standard as thought. Type 1a supernovae are white dwarfs that explode when they gain mass from a companion, always with a similar brightness, equal to the energy of billions of suns at the moment of explosion. But the data was checked independently. One team in California, the other in Australia and the United States. By 1999, articles in journals like Nature and Science confirmed the discovery. The Nobel Prize in Physics in 2011 went to these scientists. But not everyone agreed immediately. Some proposed alternatives. Maybe dust in space absorbs light, making supernovae dimmer. Or the evolution of stars changed over time. Tests rejected this. Spectral analysis showed that supernovae in the past are similar to modern ones. Let us delve into the details. The expansion is measured by the Hubble constant, 74 kilometers per second per megaparsec. This means that a galaxy at a distance of 1 megaparsec, 3.26 million light-years, is receding at 74 kilometers per second. At 10 megaparsecs, 740 kilometers per second. But for acceleration, they introduce a deceleration parameter, negative showing repulsion. In Albert Einstein's equations of general relativity, there is the cosmological constant, a term he added in 1917 to make the universe static and then rejected. Now it explains dark energy, positive vacuum energy, where emptiness gives birth to virtual particles. Analogy: the vacuum is not emptiness like an empty room, but a boiling soup where particles appear and disappear in fractions of a second, creating outward pressure. In quantum field theory, this is the energy of zero-point oscillations. But the mystery: calculations give energy 120 orders of magnitude larger than observed. It's like expecting an ocean and finding a drop. This cosmological constant paradox torments physicists. The scientific community split. Some accepted dark energy as a fact, others seek modified theories of gravity. For example, the modified Newtonian dynamics theory suggests that gravity is weaker at large distances, mimicking acceleration.
But data from galaxy clusters where dark matter, 27% of the universe, attracts and dark energy repels support the standard model. Imagine the human aspect. Perlmutter recalls how the team sat through nights arguing. We thought we were measuring deceleration, but found acceleration. It was a shock. Conferences boiled with debates. By 2000, data from the cosmic microwave background, the relic radiation of the Big Bang, began to confirm the universe is flat, with energy density exactly 1. Without dark energy, it would be less. But the accumulated data pushes us towards an unpleasant thought. Dark energy is not just an addition, but a dominant force, determining the fate of the universe. If it is constant, we await heat death, eternal expansion into cold. If it changes, chaos. This makes us wonder, why exactly this density? The anthropic principle says that in a multiverse, parameters are tuned for life. Let us add visuality. Imagine animation, galaxies flying apart like fireworks, but instead of fading, flaring brighter. The sound builds, symbolizing acceleration. Then archival footage, astronomers at telescopes, graphs with curves. Fundamental principle. Energy mass curves space, but dark energy stretches it evenly. Comparison, like elastic fabric stretched by weights, matter, but with springs pushing outward. Paradox. Why did dark energy activate 9 billion years ago? Before that, matter dominated. Reaction. From denial to acceptance. By 2005, missions like the Wilkinson Microwave Anisotropy Probe confirmed. Unpleasant thought. We know only 5% of the universe. The rest is darkness. To reach the volume, let's expand the narrative. Add more analogies, stories, details. Go back to the entry point. In 1987, Perlmutter started the project, searching for supernovae. By 98, dozens of discoveries. The strangeness, at distances of 5 billion light-years, acceleration is noticeable. Principle. Friedmann equations describe expansion with terms for matter, radiation, dark energy. Analogy, economy. Matter, like debts, slowing growth. Dark energy, like inflation, accelerating. Mystery. Why W, the equation of state parameter, -1, like for the constant. Reaction. Skeptics like Philip Peebles propose tests. Data. Baryonic acoustic oscillations. Waves of the size of 147 megaparsecs, measuring expansion. Unpleasant thought. Dark energy could be phantom, with W less than -1, leading to RIP. This is the act of discovery, from strangeness to paradox.
Part 3. Observations. Let us journey deeper into the heart of the cosmos, where the evidence for dark energy begins to stack up like layers of an ancient mystery unfolding before our eyes. Picture this. High atop the Chilean Andes, in the year 2003, astronomers at the Cerro Tololo Inter-American Observatory peer through the Blanco telescope as part of the Sloan Digital Sky Survey. What they discover shakes the foundations of cosmology once more. They map the distribution of galaxies across billions of light-years and find peculiar patterns, vast ripples in the fabric of space, known as Baryon acoustic oscillations. These are like frozen sound waves from the early universe, echoing from a time when the cosmos was just 380,000 years old, right after the Big Bang. These oscillations are enormous, waves spanning 147 million parsecs, which is about 479 million light-years across. That is a distance so vast, it could swallow our entire Milky Way galaxy thousands of times over, like a single ripple in an ocean the size of a continent. Scientists measured the size of these waves using data from over 1 million galaxies, each with masses equivalent to hundreds of billions of suns. The temperatures involved hark back to the early universe's plasma state, around 3,000 degrees Kelvin, cooling to the cosmic microwave background's current 2.7 degrees Kelvin, colder than the deepest space we can imagine. Classically, without dark energy, these oscillations should appear smaller in the distant past because gravity would have slowed the expansion, compressing the scales. Think of it like footprints in sand. If the tide is receding slowly, the prints stay close, but if it accelerates, they stretch out. The standard model without repulsion predicted a certain size for these waves based on matter and gravity alone. But the observations showed the waves were larger than expected, stretched by an accelerating expansion. Attempts to explain this with just dark matter, that invisible glue holding galaxies together, failed, because dark matter attracts, clumping things closer, not pushing them apart. Modified gravity theories, like those tweaking Newton's laws on cosmic scales, were tested but could not match the precise measurements without introducing inconsistencies in galaxy rotation curves or cluster dynamics. This was no small finding. The Sloan Digital Sky Survey covered a quarter of the sky, probing depths up to 8 billion light-years, with redshifts up to 0.5, meaning the light from these galaxies has been stretched by 50% since it left them. The energy scales are mind-boggling. Each galaxy cluster in these maps has a mass of about a quadrillion suns, radiating X-rays at temperatures of 10 million degrees Kelvin, from hot gas trapped in gravitational wells. Yet even with all that mass pulling inward, the overall structure showed expansion speeding up, as if an unseen wind was blowing the cosmic web apart. But this is just one piece. Fast forward to the year 2013, aboard the Planck satellite orbiting Earth at the second Lagrange point, 1.5 million kilometers away. Here, scientists from the European Space Agency capture the most detailed map yet of the cosmic microwave background, the faint glow left over from the Big Bang, a snapshot of the universe at its infancy. This radiation fills every cubic centimeter of space with about 400 photons, each with frequencies around 160 gigahertz, corresponding to wavelengths of about 2 millimeters. The map reveals tiny fluctuations in temperature, variations of 1 part in 100,000, like subtle ripples on a calm pond. These are the seeds of galaxies, amplified by gravity over billions of years. Without dark energy, the flatness of the universe, its geometry being neither curved like a sphere nor saddle-shaped, could not be explained. The total energy density must be exactly 1 for flatness, but visible matter and dark matter add up to only 32%. The missing 68%? Dark energy. Classical explanations, like an open universe with just matter, would show larger angular sizes for these fluctuations, but observations matched a flat cosmos only with repulsion included. Scale it up. The cosmic microwave background covers the entire sky, from a time when the universe was 1 billion times smaller, with densities 1 trillion times higher than today. The energy released in the Big Bang equates to 10 to the power of 89 ergs, enough to outshine every star in the observable universe 1 billion times over. Yet dark energy's subtle push is evident in how these ancient patterns align with modern galaxy distributions. Attempts to dismiss it with quantum fluctuations alone fail, because they predict a wildly different vacuum energy, off by 120 orders of magnitude, the worst mismatch in physics history. Now imagine the Dark Energy Survey in the year 2018, using the Dark Energy camera on the Blanco telescope again, this time surveying 5,000 square degrees of the southern sky. They study weak gravitational lensing, the subtle bending of light from distant galaxies by intervening mass, like looking through warped glass. This lensing affects shapes of over 100 million galaxies, each distorted by about 1%. Parameters here, shear measurements with precision of 0.01 over distances up to 10 billion light-years. Classically, if only gravity ruled, the lensing would be stronger, as mass clumps more without repulsion. But data showed weaker lensing, consistent with dark energy diluting structures over time. Compare, without it, clusters like the Bullet Cluster, 2 colliding galaxies with masses of 10 to the 15th solar masses moving at 4,000 kilometers per second would behave differently.
but X-ray emissions at 50 million degrees Kelvin match only with acceleration. Recent breakthroughs? In the year 2024, the Dark Energy Spectroscopic Instrument on the Kitt Peak National Observatory maps 37 million galaxies with spectroscopic redshifts accurate to 1 part in 1,000. They find the expansion rate varying over time, with Hubble parameter dropping from thousands of kilometers per second per megaparsec in the early universe to 73 today. This evolution screams dark energy, as constant density drives late-time acceleration. Scale: galaxies observed have luminosities of 10 billion suns, spectra showing absorption lines at wavelengths shifted by up to 300%. Classical Big Crunch models fail here. They predict recollapse, but data shows eternal stretch. Another line: integrated Sachs-Wolf effect in the cosmic microwave background, where photons gain or lose energy traversing potential wells. In a matter-dominated universe, no net effect, but with dark energy, a slight blue shift for late-time light, observed as temperature correlations with galaxy positions over scales of 1 billion light-years. But this is merely a small fragment of a far stranger picture. To expand to 1,500 words, weave in more narrative. Let us step back and tell the story of Adam Rees in 2010, refining supernova measurements with the Hubble telescope. He observes over 1,000 Type 1a supernovae, each exploding with 5 billion times the Sun's luminosity, for weeks at distances up to 12 billion light-years. Brightness peaks at -19.3 magnitude, visible across the universe. Without dark energy, their light curves would match decelerating models, but they dim faster, proving acceleration started 5 billion years ago. Analogy: like cars on a highway. If slowing, distant ones closer, but they are farther, roads stretching. Human element: teams work decades, calibrating with Cepheid variables, stars pulsing every few days, distances accurate to 5%. Recent: UKLID telescope, launched 2023, images billions of galaxies, measuring shapes to 0.001 precision. Early data confirms Baryon acoustic oscillations scaled up by dark energy. James Webb telescope, 2022, peers to 13 billion years back, seeing galaxies forming at redshifts over 10, masses of a billion suns when the universe was 200 million years old. Without dark energy, too much structure too soon. It allows time for dilution. Parameters: Webb's mirrors at -223 degrees Celsius, detecting infrared from 1 to 28 micrometers. Classical failures: quintessence models, where dark energy varies, tested but constrained by data to W between -1.2 and -0.8. Narrative: astronomers like Laura Federica calibrate distances using the tip of the red giant branch, stars at 8,000 degrees Kelvin. Observations build from ground telescopes like the Very Large Telescope in Chile, baselines of 8 meters, resolving arcseconds. End with: these proofs link but lead to bigger enigma.
As the observations pile up like storm clouds on the horizon, the true implications of dark energy begin to emerge, casting long shadows over our understanding of the cosmos. Let us shift our gaze to the year 2015, when the Dark Energy Survey collaboration involving hundreds of scientists from universities like Fermilab and the University of Chicago releases initial results from their massive sky scan. They have been tracking the growth of cosmic structures over the past 10 billion years, using weak lensing to map how gravity bends light around galaxy clusters. What they find is paradoxical. The universe's large-scale structure is smoother than expected, as if an invisible hand is ironing out the wrinkles that gravity should have created. These clusters are colossal, masses up to 1 quadrillion times that of our Sun, spanning hundreds of millions of light-years, with internal temperatures soaring to 50 million degrees Kelvin from colliding gas clouds. In a world without dark energy, matter would clump more aggressively, forming denser webs of galaxies. But the data shows dilution. The clustering parameter sigma 8, a measure of how lumpy the universe is on scales of 8 megaparsecs, comes in at 0.81, lower than the 0.89 predicted by matter-dominated models. This smoothing effect is dark energy's fingerprint, repelling matter on cosmic scales and preventing overclumping. Classical theories, relying solely on general relativity, falter here. They overpredict structure formation by 20%, leading to a universe too bumpy to match what we see. Now weave in the more recent threads from the last decade. In 2019, the Kilodegree Survey, using the Very Large Telescope Survey telescope in Chile, probes 300 million galaxies over 1,000 square degrees of sky. They measure cosmic shear, the distortion of galaxy shapes by lensing with precision down to 0.005. Distances reach up to 5 billion light-years, redshifts to 1. The shocking part? The tension in measurements. The Hubble constant from lensing is 72 kilometers per second per megaparsec, while cosmic microwave background gives 67, a 5 sigma discrepancy, hinting that dark energy might not be constant but evolving, perhaps is quintessence, a scalar field rolling down a potential like a ball on a hill. The most shocking discovery ties into the Hubble tension itself. In 2021, Adam Rees's team, using the Hubble Space Telescope and now the James Webb Space Telescope, refines the local expansion rate to 73.04 kilometers per second per megaparsec, with error bars of just 1.04. This clashes with Planck's 67.4 from early universe data. Why? If dark energy were simply Einstein's constant, the rates should match. But the mismatch suggests dark energy density increases over time, or perhaps early dark energy, a burst in the first moments after the Big Bang, altering sound wave propagation in the plasma at 3000 degrees Kelvin. Link it all? These pieces form a hypothesis that dark energy is dynamic. Observations from the Baryon Oscillations Spectroscopic Survey in 2014 mapped 2 million galaxies, finding baryon acoustic oscillation peaks shifted by acceleration, scales stretched by 7% over 6 billion years. Parameters? Peak at 145 megaparsecs, but observed at 152 in comoving distance. This ties to supernova data. Over 2,000 Type 1a events now cataloged, luminosities peaking at 4 billion solar units. Distances calibrated to 1% accuracy via Cepheids pulsing at 30 days periods. Extend beyond? These proofs point beyond mere acceleration to the fate of reality. If dark energy's equation of state W deviates from -1, say to -1.11, we face phantom energy, where density grows with expansion, leading to a big rip in finite time. Calculations show in 22 billion years, galaxies tear apart at speeds exceeding light. In 60 million years before that, solar systems dissolve. Months prior, planets explode. Seconds before, atoms rip. Temperatures infinite as horizons shrink. Recent studies, 2023's Euclid mission orbiting at Lagrange point 2 images 1.5 billion galaxies, measuring redshifts to 0.001 accuracy over 35% of the sky. Early data constrains W to -0.95 plus or minus 0.04, ruling out some varying models but opening doors to others. Another paradox, vacuum catastrophe. Quantum predictions give dark energy density 10 to the 120th times observed, like predicting Earth's mass as a galaxy's. String theory suggests a landscape of 10 to the 500 vacua, anthropically selecting ours. Human story? Cosmologists like Eleonora Di Valentino debate at conferences, papers citing over 10,000 references. Collaborations like DESI, Dark Energy Spectroscopic Instrument, in 2024 report expansion history over 11 billion years using quasars at redshifts 3, luminosities 10 trillion suns. These evidences point beyond dark energy and lead to multiverse ideas, where our universe is one bubble in eternal inflation, dark energy varying across. But the shocker? If evolving,
Dark energy could trigger phase transitions like water freezing, altering physics laws. This builds the hypothesis dark energy drives not just expansion, but potential instability in the vacuum itself.
Now, as the cosmic puzzle pieces snap into place with a chilling click, we step back to behold the grand theory that ties it all together, a framework that explains the invisible hand guiding the universe's fate. Imagine Albert Einstein in his cluttered office in Princeton in the year 1931, long after he had dismissed his own cosmological constant as a blunder. Little did he know that this discarded term would rise like a phoenix to become the cornerstone of modern cosmology. The Lambda cold dark matter model, or L-lambda CDM for short, is the reigning theory, weaving dark energy into the fabric of reality as that very constant, a positive energy inherent to space itself, causing repulsion on the largest scales. This theory posits that the universe is composed of 5% ordinary matter, the stuff of stars, planets, and people, 27% dark matter, which provides the gravitational scaffolding for galaxies without emitting light, and 68% dark energy, the enigmatic driver of acceleration. At its core is general relativity, Einstein's masterpiece from 1915, describing gravity as the curvature of space-time by mass and energy. But to fit the observations, we add the cosmological constant, lambda, which acts like a uniform pressure, pushing space apart. Mathematically, in the Friedmann equations governing cosmic evolution, lambda appears as a term that grows dominant as matter dilutes, flipping expansion from deceleration to acceleration around 5 to 9 billion years ago, when the scale factor was about 0.6, meaning the universe was 60% its current size. Picture it narratively. The Big Bang ignites at time 0, a singularity of infinite density and temperature, perhaps 10 to the 32 degrees Kelvin, expanding rapidly in an inflationary phase lasting 10 to the minus 32 seconds, stretching quantum fluctuations into cosmic seeds. Then, radiation dominates for 47,000 years, followed by matter for 9 billion years, clumping into structures under gravity's pull. But lambda lurks, constant at about 6 times 10 to the minus 10 joules per cubic meter, tiny yet pervasive, equivalent to the mass energy of 3 hydrogen atoms per cubic meter. As space grows, matter's density drops as 1 over scale factor cubed, radiation as 1 over 4, but lambda stays fixed, overtaking around redshift 0.75. Key physicists championed this: Saul Perlmutter, Adam Rees, and Brian Schmidt, whose Nobel-winning work in 2011 solidified lambda's return. Institutions like the Lawrence Berkeley National Laboratory, where Perlmutter's team crunched supernova data, and the Australian National University for Schmidt. Collaborations such as the Supernova Cosmology Project involved over 50 scientists, cross-checking with telescopes like Keck in Hawaii, mirrors 10 meters wide, resolving details down to 0.03 arcseconds. But alternatives abound, each with thorns. Quintessence proposes dark energy as a dynamic scalar field, akin to the Higgs field discovered at the Large Hadron Collider in 2012, with mass around 10 to the minus 33 electron volts, lighter than a neutrino. This field evolves, its potential energy driving repulsion, with equation of state W varying from minus 1/3 in the past to minus 1 today. Proposed by physicists like Robert Caldwell in 1998, it fits if W is minus 0.98, as constrained by Planck data. But problems: it requires fine-tuning the field's initial conditions to match observed density, why so small now, and it predicts slight variations in expansion history, testable but not yet detected beyond 3 sigma. Another contender: modified gravity, like F of R theories from Sean Carroll and others at the University of Chicago in the early 2000s. Here, Einstein's equations are tweaked, making gravity weaker on cosmic scales, mimicking acceleration without new energy. For instance, in scalar tensor theories, an extra field couples to curvature, altering Friedmann equations. Parameters: the Brans-Dicke parameter omega greater than 40,000 from solar system tests, but cosmic scales allow deviations.
Issues: it struggles with local tests, like Cassini spacecraft measurements in 2003, constraining deviations to 1 part in 10,000, and fails to explain cosmic microwave background polarization patterns, B modes at frequencies 150 GHz, without ad hoc adjustments. Then, phantom dark energy, where W less than -1, proposed by Caldwell in 2002 at Dartmouth College. This leads to increasing density, culminating in a Big Rip singularity in about 20 billion years, where the scale factor diverges, ripping spacetime. Energy scales: phantom fields violate null energy condition, allowing wormholes or time travel in theory, but quantum effects might stabilize. Problems: instability, fields roll to infinity, and observations from the Dark Energy Spectroscopic Instrument in 2024 cap W at -1.2 at most, with 2 sigma confidence. Philosophically, this forces a rethink of fundamentals. If lambda is vacuum energy, why does quantum field theory overpredict it by 120 orders, the cosmological constant problem? As Stephen Hawking pondered at Cambridge in the 1980s, perhaps anthropic selection in a multiverse where string theories 10 to the 500 vacua allow varied lambdas and only small ones permit galaxies and life. Eternal inflation from Alan Guth at MIT in 1980 creates bubble universes, ours tuned just right. Ekpyrotic models from Paul Steinhardt at Princeton in 2001 suggest cyclic universes where dark energy triggers contraction, but they falter on entropy buildup and matching supernova dimming curves, which show acceleration starting at redshift 1, distances 10 billion light-years. Key collaborations: the European Space Agency's Planck, with over 400 scientists, mapping temperature anisotropies to 1 part in a million, confirming lambda at 68.3% with error 0.8. Universities like Caltech, where Kip Thorne modeled gravitational waves detected by LIGO in 2015, rippling at frequencies 100 Hz, but dark energy's effects are too subtle to detect directly yet. Existentially, this redefines existence. If dark energy wins, heat death awaits in 10 to the 100 years, protons decaying at 10 to the 34 years, black holes evaporating in 10 to the 100 via Hawking radiation at 10 to the -20 Kelvin. We are transient sparks in eternal chill. Or, if varying, perhaps phase transitions, vacuum decay at speeds near light, bubbles expanding, rewriting physics. L-lambda CDM fits best, with chi-squared goodness of fit under 1 per degree of freedom across datasets. Supernova, Baryon acoustic oscillations peaking at 147 megaparsecs, lensing shears of 0.02, Hubble diagrams to redshift 2. But cracks: the Hubble tension, local 73 versus early 67 kilometers per second per megaparsec. Merely refine numbers, but rewrite the story of our cosmic destiny. The combination of Roman, Euclid, Rubin, and Lisa will create a multi-messenger map of the universe so detailed that any remaining alternative to dark energy will either shine through or be extinguished forever. We stand at the threshold where observation meets philosophy. The same force that stretches space may also stretch the limits of what we believe possible. As these missions unfold, they will reduce the unknown from 68% to mere fractions, yet the mystery will deepen. Why this particular value of dark energy? Why now? Each new photon captured, each new gravitational wave detected will echo the same existential challenge we began with. What if everything we thought we...
Part 7. Main questions. As our journey through the shadows of the cosmos reaches its zenith, the weight of dark energy presses upon us not just as a scientific curiosity, but as a profound upheaval in the very essence of existence. Picture a philosopher-astronomer gazing at the night sky in the quiet hours before dawn, pondering the invisible force that shapes everything we see and far more that we do not. The deepest conclusions emerge when we consider how dark energy reshapes our grasp on reality itself, turning the universe from a predictable machine into a dynamic enigma where emptiness holds the reins of destiny. At its core, Dark energy challenges the bedrock of physics, the conservation of energy and the nature of vacuum. In the Standard Model, energy cannot be created or destroyed, yet the cosmological constant implies that as space expands, more dark energy appears, maintaining constant density. This seems to violate intuition, like a bank account that grows interest without deposits. Quantum mechanics offers a glimpse. The vacuum seethes with virtual particles, their fleeting existence contributing positive energy that repels. But the paradox bites deep. Theoretical calculations predict a vacuum energy density 120 orders of magnitude too large, enough to have blown the universe apart instants after the Big Bang. Why this tiny observed value, precisely tuned to allow galaxies, stars, and life? It is as if the cosmos were calibrated with exquisite precision, raising whispers of design or selection in a vast multiverse. This ties dark energy to other cosmic riddles, like the flatness problem. Why is the universe's geometry so perfectly balanced, neither collapsing nor flying apart too quickly? Without dark energy's counterbalance, early fluctuations would have led to a curved cosmos, but observations from the Planck satellite show curvature parameter omega k at less than 0.001, flatter than a billiard table across 46 billion light-years. Link it to inflation, that explosive growth in the first 10 to the minus 32 seconds, smoothing the universe but leaving quantum scars as the cosmic microwave backgrounds ripples. Dark energy might be inflation's echo, a remnant field that lingered, or perhaps a new phase where the Higgs field, responsible for particle masses at 125 giga-electron volts, interacts in unseen ways. Unresolved paradoxes abound, chief among them the coincidence problem. Why does dark energy dominate exactly now in the era of intelligent observers? Matter density drops with expansion, but dark energy stays fixed. Their equality at redshift 0.33, about 4 billion years ago, seems suspiciously timed for life to emerge. Is this anthropic, where only such universes breed thinkers to ponder it, or a deeper law? Another thorn, the Hubble tension, where local measurements via supernovae and Cepheids give 73 kilometers per second per megaparsec, but early universe inferences from Baryon acoustic oscillations yield 67, a 4.8 sigma mismatch, suggesting dark energy evolves, or new physics lurks, perhaps neutrinos with unexpected masses around 0.06 electron volts, or sterile varieties. Boldly, let us venture scientific assumptions that push boundaries. Suppose dark energy is not constant, but quintessence, a field akin to those in grand unified theories, coupling to dark matter, 27% of the cosmos, inferred from galaxy rotations at 200 kilometers per second beyond visible edges. This could explain why dark matter halos, masses 10 to the 12 solar units, formed the scaffolds we see. But with dark energy's influence waning, perhaps triggering a future where gravity wins, leading to an oscillating universe with cycles every 100 billion years. Now, envision 2 to 4 scenarios for what lies ahead, each grounded in data, yet daring in scope. First, the steady state. Dark energy as eternal constant. W equals -1. The universe expands forever, cooling to near absolute zero in 10 to the 14 years. Stars exhaust fuel in 100 trillion years. Protons decay in 10 to the 34. Black holes evaporate in 10 to the 100 via radiation at 10 to the -20 Kelvin. Reality fades to dilute soup of photons and leptons. Entropy maximal, the heat death, where time loses meaning in uniform chill. Philosophically crushing, all achievements, all life dissolve into irrelevance. Second, the phantom path. If W dips below -1, say -1.5 as some supernova data hints with 2 sigma, density grows, acceleration runaway.
In 22 billion years, the Big Rip commences. Milky Way shreds first, stars flung at near light speeds. 60 million years prior, solar system unbinds, Earth-Moon distance exploding exponentially. Months before end, planets disintegrate under tidal forces. Seconds prior, atoms rupture as strong force yields, quarks freed in a final frenzy. Temperatures soar to infinity as horizons collapse, space-time itself torn. Bold assumption, this could birth new universes through quantum tunneling, a cosmic reproduction. Third, the decay scenario. Dark energy as metastable vacuum, like a ball atop a hill. Quantum fluctuations could nucleate. Perhaps new physics like early dark energy from Nima Arkan Hamed at the Institute for Advanced Study, injecting energy at recombination, altering sound horizon by 7%. This makes us rethink the basics of space, time, and causality. Is the universe fine-tuned or one of many? Dark energy challenges causality, as acceleration creates event horizons, information lost beyond 46 billion light-years co-moving. Theorists like Lisa Randall at Harvard explore extra dimensions in brain world models from 2000, where gravity leaks, mimicking dark energy, but constrained by collider data missing Kaluza-Klein modes above 1 tera-electron-volt. All alternatives grapple with the same data. James Webb observations of early galaxies at redshift 12, masses 10 billion suns when the universe was 400 million years old, fitting Lambda, but straining without it. This theory, dominant yet questioned, forces philosophical reckoning. Why this universe? The anthropic principle whispers multiverse, but testable? Perhaps not, veering to metaphysics. To expand, narrative of Einstein regretting Lambda, then quantum pioneers like Dirac predicting large numbers coincidence, why Lambda so small now? Analogy, dark energy like compound interest, small but compounding over cosmic time. Human, conferences like Cosmobrains in 2020 debating. Alternatives problems, loop quantum gravity from Carlo Rovelli at Marseille, quantizing space, but no clear dark energy emergence. This part builds to existential depths.
Now the stage widens to the horizon of tomorrow, where the invisible force we have chased through decades of data begins to reveal its final secrets through the eyes of machinings yet to be born. Imagine engineers in clean rooms across Europe and America in the year 2025 bolting together the mirrors of the Nancy Grace Roman Space Telescope, a 2.4-meter giant set to launch in the year 2027. This observatory, named after the mother of the Hubble Space Telescope, will scan 2,000 square degrees of sky every few months, measuring the shapes of more than 1 billion galaxies with a precision of 1 part in 10,000. It will hunt for the subtle distortions caused by weak gravitational lensing and map the growth of cosmic structures over the past 11 billion years, searching for any hint that the dark energy density is slowly changing rather than staying perfectly constant. Recent breakthroughs already give us grounds to expect dramatic answers within the next decade. The Dark Energy Spectroscopic Instrument, perched on the 4-meter Mayall telescope at Kitt Peak in Arizona, has already mapped more than 40 million galaxies since it began operations in the year 2021. By the year 2029, it will have charted the expansion history with such detail that any deviation in the equation of state parameter from exactly -1 will stand out like a flare in the night sky. Early results already whisper of a possible slight evolution, tightening the noose around static models and opening the door to dynamic fields that could either fade away or grow stronger. Look further ahead to the year 2030, when the European Space Agency's Euclid mission, already in orbit at the second Lagrange point 1.5 million kilometers from Earth, will have completed its 6-year survey of 15,000 square degrees. Euclid's near-infrared camera and visible imager will measure galaxy shapes to an accuracy never before achieved, constraining the dark energy equation of state to within 1%. If the data show even a tiny drift, it will confirm that we are not dealing with Einstein's simple cosmological constant, but something far more alive, perhaps a rolling scalar field whose potential energy is slowly unwinding like a cosmic spring.
Picture the Vera C. Rubin Observatory on Cerro Pachon in Chile, scheduled to begin its legacy survey of space and time in the year 2025. With its 8.4-meter mirror and 3.2 billion pixel camera, it will photograph the entire southern sky every 3 nights for 10 years, discovering millions of new supernovae and tracking how their brightness evolves over cosmic time. This flood of data will allow astronomers to build a 3-dimensional map of the universe's expansion with unprecedented resolution, revealing whether dark energy's grip is tightening or loosening as the cosmos ages. Even more ambitious technologies are on the horizon. In the year 2035, the Laser Interferometer Space Antenna, a trio of spacecraft forming an equilateral triangle 5 million kilometers on each side, will begin listening for gravitational waves from the dawn of time. These ripples in space-time stretching and squeezing at frequencies 1,000 times lower than those detected by ground-based observatories could carry echoes of the very moment dark energy first dominated. If early dark energy left an imprint during the first moments after the Big Bang, LISA will hear it as a faint background hum, confirming or ruling out models where the repulsive force was stronger in the infant universe. Ground-based experiments are also racing forward. The Cosmic Microwave Background Stage 4 project, a network of telescopes in Chile and Antarctica, will map the afterglow of the Big Bang with 10 times the sensitivity of the Planck satellite by the year 2030. It will measure tiny polarization patterns at frequencies around 150 gigahertz, searching for signs of primordial gravitational waves that could have been amplified by varying dark energy in the first trillionth of a second. If those patterns appear stronger than expected, it will point to a universe that was born with a different balance of forces than we currently assume. These instruments are not just tools, they are time machines that will let us watch the cosmic drama unfold across 14 billion years in a single decade of observation. Imagine scientists gathered in control rooms, screens glowing with real-time data streams as the first hints emerge. Will dark energy prove constant, locking us into an eternal, ever-colder expansion? Or will it evolve, perhaps fading and allowing gravity to reclaim dominance in the far future, or perhaps intensifying toward a catastrophic rip? The possible breakthroughs are staggering. Within 15 years, we may know whether the Hubble tension is real or an illusion, finally deciding if the early and late universe speak the same language. We may detect the first direct signature of vacuum energy through precision measurements of atomic clocks in space, or through tiny shifts in the fine structure constant over billions of years. Some theorists even dream of laboratory tests using ultra-cold atoms or high-energy lasers to mimic the conditions where dark energy might reveal itself on small scales. Scale these expectations to the ultimate cosmic maximum. In 100 billion years, if dark energy remains constant, every galaxy outside our local group will have vanished beyond the event horizon, leaving our descendants, if any, in a lonely island of stars surrounded by absolute darkness. In 1 trillion years, the last stars will burn out, and in 10 to the 100 years, even black holes will evaporate through Hawking radiation, leaving a sea of photons cooling toward absolute zero. Yet, if dark energy strengthens even slightly, the timeline collapses. Galaxies will be torn apart in 20 billion years, solar systems in 60 million years, planets in months, atoms in the final seconds. Conversely, if dark energy weakens, distant galaxies could slow, turn around, and begin falling toward us, setting the stage for a future big crunch or cyclic rebirth. Either path forces humanity to confront the deepest questions. Are we alone in this accelerating void? Will our descendants ever escape the solar system before the stars go out? Does consciousness have a place in a universe marching toward heat death or violent disintegration? Recent breakthroughs give us grounds to expect that the next generation of telescopes will not